This is week 11, and as far as I remember, this is probably the last laboratory session that we are going to have. And this week we will be concluding our discussion with the state space methods, or the whole representation and whole state space world. So basically, we will also have a final session that will be basically a solution to some example questions for the final exam that you're going to have, basically. But I guess I'm going to be uploading it from the last semester, because that had a Turkish and an English version, so it's quite handy. It was in a classroom. I hope that will help you out. I will provide the necessary links. And then if you still have some questions, please feel free to contact me over Discord for this course, and I'll be happy and try to explain you or help you out in certain areas. So let's go into the state space world. Now, last week we were talking about, or last video we were talking about the frequency domain. Now, let me actually remind you that even though the frequency methods and the state space session takes only 1 week per lecture, so week 10 and week 11, they are quite important. Don't skip them, because in your final exam, most probably, or anywhere about this lecture, you will face them. You will have some questions about them. So there's this interesting fact about this course where we are spending so much time on the time domain methods, PID, PIPD, anti-windup, and stuff like that, that it doesn't take that much to cover the frequency methods and state space methods. So as far as I know, this will be updated in the upcoming semesters, but this is a sort of a flow of this plan that we have now. So I'll highly suggest you to focus on week 10 and week 11 frequency domain methods and state space, because even though they take just 1 week, they're quite important. In fact, they will be probably heavily addressed in the final exam, so be aware of that. We will have a quiz, and the quiz will be about week 10, so frequency domain. Let me also announce that. And yeah, let's dive into state space. Now, before we dive into state space, I want to make the following statement. Actually, the frequency domain is just a change of perspective that we did in the last video. The state space topic is also just a perspective change. Basically, we're addressing, again, the same type of systems. They have, again, the same behavior, the dynamic behavior. They are modeled with using differential equations, but here we use the differential equation a bit more than transfer functions, because now we don't look at a system just as inputs and outputs. What we are doing here now is we're looking at its internal states, sort of. And the state space is called, therefore, state space, because we have some internal states of the system. We are looking in the internals of the system and the inputs and outputs. So therefore, it's a more detailed mathematical model-based topic that we're going to basically cover now. So for any system, any LTI system that we address in this course, we say that it can be represented with an nth order differential equation. But the problem with an nth order differential equation is that it is a high order differential equation, and solving it takes some mathematical complexity. Since it's linear, it's not that bad, of course, but we would rather have something called the state space model, which is basically, again, the same differential equation. Nothing changes. It's the differential equation. But instead of having an nth order single differential equation, we are converting this into a much simpler, in quotes, model, which has n differential equations of order 1. And that's basically it. If you know the basics of this, state space is quite fun and quite easy, in my opinion. Let's see if you will think about what you're going to think about the state space now. Now, the state space model itself is basically, instead of having y to the nth derivative sort of thing. So that was kind of the notation. So nth derivative of y plus n minus 1th derivative of that plus y derivative plus y equals u is kind of our differential equation of a linear time invariant transfer function. What we're trying to do is we're trying to come up with f1, f2, dot, 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 fn sort of differential equation. So n differential equations of order 1. Each of them should have just derivative 1, no higher derivative than 1. So you can see there are lots of differential equations, and we will also have lots of variables here. What we are basically doing, therefore, is we're using the matrix notation because it becomes handy. So what we're going to do is we're basically going to do the following. We are going to define x1 equals y, for example, because that's one variable that we care about. We are trying to solve it for y, for example. Now, each time we have a derivative, x1 derivative, which is basically y derivative here, we are going to add another, or we are going to define that derivative as a new variable. Now, you can see that this is going to generate a pattern because we will have y double derivative sort of thing, which we will call x3, and then x3 derivative is going to be basically y to the third derivative, and then that's going to be x4, and it will go on like that once we reach basically the highest order term, yn. Now you can see that this doesn't only define each derivative as a new variable, this also generates a dependency of variables, because you can see that in order to be able to use this, we need to ensure that x1 derivative is in fact x2, and that the derivative of x2 is also x3. If this equation doesn't hold, then our differential equation will not be the same anymore, because these are dependent variables on each other. So they have kind of a relation to each other. These are not arbitrary, basically, definitions. These are definitions that need to be chosen in a certain way. Therefore, we will have basically n amount of equations, because x1 derivative should be x2, x2 derivative should be x3. This goes on until we reach the differential equation itself, but then this differential equation can be substituted with these new defined variables, and it will be converted into a first-order differential equation. So that's basically the whole point of using this state space model here. Once we've done that, we end up in xn derivative is something plus u, because this is the only equation with this notation where we have u, because everything is just a redefinition of the derivatives of our single y variable here. So therefore, we generalize this notation. We define a variable called x, which is going to be the state variable, and we dump in all the definitions that we had. So that's going to be basically this one here, xn. So this is basically our vector of unknowns or states. Now, when we take the derivative, we're talking about basically the matrix notation, x1 derivative, x2 derivative, and so on and so forth, xn derivative. So that's going to be it. Now then, we can see that there's a certain relation between the derivatives and the state space variables. So we can basically define this as the first row of the following matrix. We can say x1 derivative is basically 0, 1, 0. It goes on like that, 0 times x. And when we do it for x2, we'll see that this is basically 0, this is 1, up to xn minus 1. So dot, 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 xn minus 1 is going to be 0, 0, 0, everything is 0, but the last entry is going to be x. Now this is a certain pattern. Then we will have xn, which is the actual differential equation here, and it will be a linear combination of the rest of these variables here. So this will also be depending on something, but this row is a special row here, times x. Therefore, since we have this relation, and you can see there's basically a hidden zero vector here, 0, 0, 0, 0, and then there's a identity matrix here, so there's a special structure here. What we can do is we can say that x derivative is basically a times x. And then, of course, we have plus bu, where we can determine which row is basically influenced by the input, and that corresponding coefficient is then also in this matrix B. So this is basically the first portion of our system notation here, or the differential equation. And the last thing is to have an output equation, because you can see we have an input u, which is the classical input of a transfer function. But then we have something called x, which is basically internal states in this case. And then we need an output, because we're interested in the behavior between an input and an output. So the output is basically this one here, based on this one here, basically. And the reason for that is, since we have a vector, and since x1 is equal to y, what we can do is we can generalize this as 1, 0, 0, dot, 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 0 times x plus 0u. For this special case, it seems like this would be the output equation, 1, 0, 0, 0, 0 times x, because this will generate x1, and we don't add any input at all. But the general notation then becomes y equals cx plus du. Yeah, so for a transfer function, we can acquire a state space model. Let me delete everything here. That looks like this, where x is going to be an element of Rn times 1, basically. So it's a vector in n times 1. So we have n elements here. Then the A matrix here, since this is n by 1, the derivative doesn't change. The derivative itself is also going to be in n times 1. So it's going to be a column vector. And if this is n by 1, this is n by 1, A should be n by n because of matrix multiplication. So this is n by n. Then we can see that u should be scalar, because u is just an input, 1 by 1. And if this whole thing is n by 1, this is also n by 1. In order to be able to add bu to these terms, and if u is 1 by 1, it seems like b should also be n by 1. So b is r n by 1. Now, what about the output equation, y? I will most of the time call this the dynamic equation, and this one the static equation or the output equation. Because you can see here, we don't have actually memory. This is not a differential equation. This is just a relation, and it holds for all time instances. At any time instant, you can just use that u value and that x value and combine them, and you will get that time instant y output. But here, you need the previous states of x, or this is basically a dynamic equation because it's a differential equation. You need an integral over a certain time interval, and that's the dynamic equation. So that's the dynamic part of the system, and that's the static part of this representation here. Now, therefore, we know that we have only one input and one output. So y should also be scalar. So I'm just examining this notation here. You should do that as well. And then we can see that u is also something that is scalar, because we've already talked about that. So Therefore, if U is also a scalar, then what we end up in is we actually have a scalar here and a scalar here. So what is the size of D? Well, basically that's also scalar. So D is also scalar. There we go. What about C? So since X was n by 1 and Y is 1 by 1, this should be 1 by n times n by 1 to have a scalar. So C is going to be R 1 by n. So if we would have a MIMO system, of course, C, D, B would change, because this is basically amount of inputs. We have 1. This is amount of outputs. This is also 1. This is outputs times inputs. So this is a scalar system, because D is basically the direct term between Y and U. It doesn't depend on X. So if X is 0, for example, you get directly Y equals DU, and Y divided by U is basically D here. And you can see if you have single input, single output, D is going to be scalar. If you have multi inputs and multi outputs, then D will be a matrix basically. But let's just use the scalar version here, because it's not going to be a topic of our course. So now we have all the dimensions, which is quite important. You need to know this stuff. So yeah, that's basically it. We have the vector sizes here, and this is going to be our sort of transfer function, but it's going to be a matrix notation. We call this state space. So for example, we have a system here which has these A, B, C, D matrices. I can see that these are scalar and it's 0. I can see that this is 1 by 2, this is 2 by 1, this is 2 by 2. All this stuff explains to me that the system is a second order system. So if I would have converted this somehow into a differential equation, then into the transfer function, I would end up in a second order transfer function. So it's important to know your state space representation, because it tells you a lot actually. So now I need to also tell you the fact that we can use the Laplace transform here, sims S here, and we can look at this as just a scalar. So if I take the Laplace transform of x dot, it will become sx minus x0, the initial condition. But since this is a transfer function, the initial conditions are set to 0. Then we're ending up with this sort of equation here. If I rearrange it a little bit, I get to this one here. Now we have common term x, so let me just get rid of this part here. But be aware that A is basically a n by n matrix. In order to be able to do this subtraction here, S is not a scalar term. This is S times the identity matrix here. So that's the important part to note here, because otherwise we're not able to do this. And S times X is also basically not defined. This should be S times the identity matrix here. Or we could say in the Matlab notation, we could say S dot times X. So what this means is this is element-wise multiplication. Either you're going to multiply it element by element, so each x1, x2, xn will be multiplied with S individually, or you're going to use this notation, which makes mathematically more sense. So I would rather stick with this one instead of this one, because this is just Matlab specific. Well, you cannot multiply from the left with a scalar if you have a vector. So yeah, therefore it should be identity. So when we end up with this, what we can basically do is we can say that we are going to multiply with the inverse from the left, because it's matrix operations. So the inverse of this times BU is going to be our equation here. Now then, we also have the static relation here. I can just basically use this x, substitute it into this one here. So let me just take this part and substitute it back in here. And I can also factor out u here and in fact divide into u. And there we go. This is something familiar. It depends on the Laplace variable s. It is a fraction of output divided into the input. Therefore, I could say that this is the transfer function equivalence of the system. So by just using the dynamic static equations that we have at hand and using the Laplace transformation and rearranging stuff gives us the expression for the transfer function. What we can do now is we can just substitute a, b, c, d into this equation here, and we can get the transfer function. So I'm going to do exactly what I said. Let's define a, which was what? Let me just put this in here. So a is going to be 1, 2, and then 1.4142, 2.8284. And we have b, which is 2 and -1. And then c is 1, 0. And d was 0. So there we go. Now, we have the matrices here. We have that. I'm just going to get rid of this whole thing here, and I'm going to call this GS. So, yeah. And we know what n is. N is going to be size a,1 or a,2. It doesn't really matter. So, because A is a square matrix, I can just use any dimension of size A. You know that the size A is basically a two-dimensional thing here. If you call it with row and col, it gives you number of rows and columns, size A. Or you can just request one dimension here, or the second dimension, or even the third dimension, and so on and so forth. So I'm just basically requesting any dimension and just use that as the order of the system. And yeah, let's call it GSS like this. Let's run this. Now we have GS. Let's see what it is. GSS actually. There we go. Now, it makes sense that we have some S squares in here because it should be a second order transfer function. Let me use simplify an even fraction maybe on GSS. And then maybe pretty GSS. Now, this is something interesting, and this was intentional. You can see that actually GSS is not a second order transfer function. It is just an integrator with coefficient 2, so 2 divided by S. And let's see what Matlab says us, because we can define a state space model, a system using the state space model. This is basically the equivalent of TF, where you provide num and then. What we do here is we give the matrices and we say that we are defining a system. So now we're able to define systems using these two methods. SS is going to be the state space, TF is going to be the transfer function. And keep in mind that both are basically different perspectives, but they are the same. So here I'm just looking at the input and output. Here I have also some internal information. So if I do this and run this back again, maybe twice because of my environment here, you can see it also shows us a nice representation. If you're new to state space, this helps you out a lot. You can see x1 derivative depends on 1 times x1, 2 times x2. x2 derivative is 1.414 x1 plus 2.828 x2. And the first equation has 2 times u, and the second equation has minus u in it. And then the output is basically y is equal to x1. And that's basically it. This is a continuous time state space model. It's nice to have this nice output if you're near to it. So then what we can do is we can pass it to a TF. So we can convert it into a transfer function. Now, Matlab doesn't tell us that this is 2 divided by s, which is quite interesting. Now, if you use Matlab, just define A, B, C, D, and then you just use TF, you see that this is, in fact, a second-order transfer function. But you can immediately see that there's a 0 term here, because 1.7 times e to the power of minus 15 is basically 0. And you would end up in this one here. So what happens if we look at it in the ZPK form? Is that going to help us out maybe? And you can see that, in fact, we can see that s minus 3.828 is a common term of the numerator and denominator. So I've basically chosen a tricky example to exemplify the state space model here. So basically, telling you that the conversion is like this. You can use this to convert it into a transfer function, or you can just define it with SS and TF to see what it is. It's quite easy, but the important part is what happens if there's a special case. Now here we can see that Matlab doesn't get rid of this pole zero cancellation, sort of, and you might guess why. All the knowledge up to this point adds up here, and you can see that this is a right half plane pole zero cancellation. And we've talked about this. We've talked about right half plane pole zero cancellations, that they are dangerous because this will never happen in real life. They will not be on top of each other, and it would cause some instability. So this system, if this is a system, if this is not a mathematical thing here, if the system has, in fact, these poles and zeros, Matlab doesn't cancel them out, so you can see that there is something wrong with this system. So, yeah. Now, well, actually, this system is just a pure integrator. It's not a second-order system, and the reason for that is basically we have a certain relation between the first row and the second row. You can see that there's 1, 2, and there's 1.4142, 2.8284, which is exactly twice as 1.4142. So there's something going on here. So in order to demonstrate that, let me just take these coefficients and write it down. So x1 derivative is going to be x1 plus 2 times x2, and then we have plus 2u, I guess. Plus 2 times u. Was it 2? Yeah, there we go. So this is the first equation. The second equation is basically 1.4142 times x1, and then 2 times 1.4142 times x2 minus u. So you can sort of see that there is a scalar here. So we can see that we have a factor 1.4142 here, and this was minus u here. Minus u here. Yeah, actually, we know also what 1.42 is. Square root of 2, actually. So we have an extra term, square root of 2 here. So we can kind of have this scalar here, and x1 plus 2 times x2, and then minus u. It's kind of the same equation, or the same row information in our state variables as it just repeats the first row here. The important part, of course, happens here where we have a where we have 2u and then minus u. These are not aligned, at least. Maybe that's going to help us out, but you can see there's something fishy going on here. We have x1 plus 2 times xu, x2, and the same is going to be here. Of course, this doesn't mean that this is very bad, but it means that the row information in A is not unique. So there's just a scalar factor, a scaling factor here, and we'll see what it's going to do for us. But if we pick up on square root 2, maybe Matlab can then help us out. So if we say, instead of saying it's numerically this, what might happen if we define A with the square root version here, instead of having the numerical version here? Let's see if Matlab picks up on that. So run it twice. Nope, it's still insisting that there's a right half plane pole zero cancellation, whereas the symbolic tool here recognizes this. Of course, we should also define it like A is square root here 2. We should define it in symbolic, or convert it into symbolic at least, because A here is still numeric, as you can see. But if you define it like this, you'll see it picks up on that. You can see square root of 2, 2 times square root of 2. And the symbolic version, or symbolic toolbox, uses this, and it seems like it's just converting it to 2 divided by s. So we actually see that the system here is a first order system, because we see that there's a right half plane pole zero cancellation. So compare the step response of them. So let's look at the step response actually and see what's going on. But we already suspect that it should basically be a ramp response. So let me create a figure, and let me have a subplot. Let's have 3 rows, 1 column, and the first one of them should be this one here. Hold on, grid on. So the nice thing about SS here, about line 14, is that we can use the step function here and just calculate whatever we want. So I'm going to do something interesting in order to simulate state space models. And that's going to be the following. I want to acquire the states here, the internals of the system, and I want to apply step to it. So let's have A, B, C, and D. If I call it like this, I won't be able to acquire the states because I'm directly feeding the transfer function here, or the model itself. And since C and D just generate Y as the output, I'm just going to observe the output here. What I really want to do is I just want to change this. When you remember the dynamic part of this system, I just want to see what the dynamic part generates here, because we just have x derivative equals ax plus bu. I'm only interested in this equation. So basically my output then that I've basically come up with, let's say y tilde or y bar, is going to be x. So I can define my own state space that shares the same dynamic equation, but I'm changing the static equation, because I can toy around with the static equation. I can toy around with the output. Because I have the internals, I can generate the system back again with using the system C and D matrices, or I can just come up with my own C and D matrices in order to look what, for example, X is. If you define a state space model that looks like this, what you're going to do is you're just going to define a identity matrix N, because we have Ix plus 0u here. So I'm just doing mathematical stuff here. Of course, this 0 should be a n by 1 0. So zeros n by 1. And the reason for that is I'm going to have n states as the output. So it's a n by 1 system. And outputs 1 input. And the outputs are basically the states. So if you are kind of confused with this stuff here, what you can do is you can just open the Simulink, just drop the state space model, and try to, or just construct this state space model on your own and then simulate it. But what I'm basically trying to do is I'm setting the output equal to the states of the system because I want to look at the states. So once I've done this, I can just plot the first state, Tx, I suspect it should be the first column here. Let's have red and then line with 2. And let's call this maybe x1. Let's have the next one here, the second one, and second one. So what I still can do, looking at this, is I can still combine x1 and x2 to generate my output here. So y can be equal to c1 times x1 plus c2 times x2 plus d times u, which is basically 1, and d is 0. So therefore, I'm just going to generate the third one here, which is basically going to be the output, and which I'm going to call y. So let's run this. Of course, I didn't change the colors. Let me change the colors. There we go. Now, what we're seeing here is the following. The first one is the first state. So this is x1 versus time. And then we have x2 versus time. And you can see that basically they are kind of the same, but this one is not stable. This one is also not stable because S is marginally stable. It's at the origin, and we cannot call it stable because it is a ramp function, so it's unstable. The second, the pole zero cancellation was also unstable, so that one is obvious too. And the result is just basically x1. Because we don't care about x2, and it doesn't have any effect on the system, we are basically not seeing x2 in the output, or it's not the sum or their linear combination here, because the C matrix has 1, 0. If I change this, for example, to 1, 2 here, then the whole system is going to change, and the output is going to change. And you can see it's an unstable transfer function, but you can see that it is quite different from the instability that we had before, because, well, we now have a system that has both the this part here and the S term here, so there are basically two combined in this result here. But this is not the important part that we're focusing here, but it might be the case where you can see that your system has kind of a internal pole zero cancellation. That means that you have a pole zero cancellation and the order will not match. Even though your matrix is 2 by 2, you will end up in a first order system. So this opens up the following question: is ABCD unique? Can I come up with something else that has basically the same transfer function? And is the state space model unique to a system? First of all, the transfer function is unique, but the state space model is not. So you can come up with numerous ABCD pairs that represent the same transfer function, but they will all represent the same transfer function. So 2 divided by S is going to be eventually the transfer function, but you can have different ABCD pairs. For example, I don't want to look at the system like this, so let me just comment this out. Maybe I might use it. Instead of doing this, let me just clear and show that. So let me change this to 0, of course. So run 1, there we go. I can construct my own state space model. I can come up with a better one than that. And let's try to do that. Well, if we have something like y divided by u, and if this is 2 divided by s, what I can do is I can just state the following, that s times y is going to be 2 times u, and this means that y dot is equal to 2 times u. And luckily, I can just say x is going to be equal to y, which generates me the following here, 2 times u here. So that's basically it. And y is equal to x. Why did I use this? Well, something derivative equals 2u. So it's quite easy to just choose y equals x, or x is the same. So x dot is equal to 2u. So this means that x dot is equal to 0 times x plus 2 times u. And this is basically 0 times u. So I'm using the same notation here. When I look at this, I can come up with a equals 0. Since it's scalar, I don't need to define anything else. B is equal to 2, C is equal to 1, and D is equal to 0. Now, this one is a scalar ABCD pair. The reason for that is that the system is a first-order system. Therefore, I don't have a matrix. I have just scalars. And the same holds here. I can still have x dot equals ax plus bu, y equals cax plus du. I can still have that. So, well, I can also define the transfer function as I would do it. So let's do it. And let's look at cis. And let me get rid of this part. So you can see it kind of represents the same. There's no dependence in that. But then we have 2, and then there's 1 and 0, and this is our system. Now I can basically convert this one into a transfer function and see what it's going to show us. There we go. Now you can see I can have basically a model that looks like this. Let me get rid of this. So ABCD can be chosen like this, and it will end up in 2 divided by s, or ABCD can be chosen like this, and it still ends up in being 2 divided by s. So this is kind of the point that I want to make here. You can have numerous ABCD pairs, but you will eventually, if it's the same system, if it's modeling the same system, you will end up in the same transfer function. Transfer function is unique, ABCD is not. And the non-uniqueness, or the infinite amount of state space models, can be defined with this equation here. So I'm basically defining a family of ABCDs. When BC multiplication 2 holds, it will always end up in the same transfer function. Why am I doing this? Why am I telling you this? Well, if you look at this, so let's just focus on the scalar version that I've done here. So A is equal to 0. So let's substitute that in. So the inverse of I is going to be I, but the only difference here will be that I'm just having this divided into S. So this inverse is gone, basically. And we can see that D is 0 in my definition, so let's get rid of that. Now, since this is basically just 1, we have C divided by S times B, but this is basically, or actually, C times B divided by S. So I've converted that into this, and you can see that my condition here was to have the multiplication of C and B to be equal to 2. If that's 2, then this is basically the numerator. If the numerator is the same, then the denominator is fixed to S, then you will end up in the same transfer function. So square root 2, whatever you want, 1, 4, you can just choose a value for B and then calculate C and come up with different ABCD pairs that still result in the same one. And it doesn't have to be scalar. It can also be this one here. And you can see, I guess, C times B here, if we have these definitions, C times B still is 2. So you can come up with vectors that kind of has C times B2. So let me generalize it into the vector case. You need to have the accurate order here. If C times B is equal to 2, C and B being vectors doesn't even change anything. You can just come up with the zero matrices here, and you can change CB as you wish, and you will end up in the same transfer function. So that's quite important to note here. And we also see that the differential equation that we have at hand here, which is basically x derivative is 2 times u, and y is equal to x, tells us something. You can see that this is basically dx divided by dt is 2u, so you can just use 2 times u dt, and x will be basically the integral of u dt. And that's basically it. So the output is 2 times the integral u dt. So it's an integrator times 2. So we can acquire the information from this one too. So yeah. Now, we came up with a state space model. We've seen that the state space model is not unique. We have multiple of them, but we will end up in the same transfer function if it's modeling the same system. So let's actually check something else. We have something called the controllability of a system. Let's see if the controllability matrix is there. If you have something like that, so let me get rid of this. Let me comment this out. So the controllability matrix phi c is something that is used to see if we can basically assign poles as we wish. So it goes on like this. You create a matrix of B and then A times B and then A times B until you reach basically n columns here. Since n is 2 in our case, we just have 2 columns here. And this is going to be the controllability matrix here. And we will use the controllability matrix in a moment when we progress a little bit more to design a controller. So in the state space world, if you have a state space model, and if you're trying to design a controller, the controllability matrix will be step 1 to check if it can be inverted or if it's not singular, if its determinant is different than 0, all these mean the same basically, then we can assume that we can assign the poles as we wish. But more to that in a moment, but we can see that this phi c is going to be something special here. So phi c, and there we go. If you look at the determinant of phi c, you will see it's 0. You can look at its rank. It's not full rank. If you try to invert it, you will see it's not invertible, infinite, infinite. It's a singular matrix, and this will cause some issues. So if you have this, if you have a not controllable system, if the system is not controllable, at least not fully controllable, then you will end up in issues, and I will talk about that in a minute. So we have a special system. We have talked about that. Let's move on. So what we can do is we can basically look at the transfer function and come up with a controller, and then design a state feedback controller to come up with a controller. So let's actually compare these two. I know that the transfer function is 2 divided by s. If I'm going to define a transfer function, then I would basically do the following. So let me just move this down here. So sims s, sims k, real, and then TSS will be k times GSS. And I'm basically designing a p-type controller to the system. Since I can convert it into a transfer function, I can do whatever I want. So this is basically it. And then we will have num and then call num then TSS, and then we'll see what the denominator looks like. So s plus 2k. Now, it seems like when I have this system and a p-type controller, when I want to assign a certain pole, let's say it's going to be 4, I can choose k equals 2 and I'm basically done. So there's this relation where basically K should be equal to pole divided by 2 here. And that's it. You can choose any pole, divide it by 2, use that as a gain, and you have the pole assigned. Because it's a scalar system, it's quite easy to come up with a controller, especially a p-type controller. And you can see we can assign the whole real axis because it's a first order system. We have one parameter, one pole to move, and that parameter can move the pole as we wish. So that's nice. So what about the state feedback controller, which is basically the easiest controller in the state space world? It's basically the p-type controller of the state space world, and we call it the state feedback controller. And all it does is it uses basically this equation here. And this equation is a simple equation that is basically a scalar multiplication here, a dot product sort of, that goes on like this. So we have k2 times x2, and then dot, 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 kn times xn. So what we're basically doing is we have a state space system. We have n states. We're taking the linear combination of the n states and feed it back. So now, instead of having something like a classical feedback setup, like k times gs, and then like the setup that we always have, now it looks a little bit different. We will have basically an integrator here. This is called basically x derivative, then the integral will give us x, and we are going to have basically this black box here. Let me call it the state space or ABCD model here. And so that's basically it. So this is input, this is output here. And what we're trying to do now is we need a certain x, which we don't have at the moment. Let me just show it like this. So this is kind of an x here, and we have multiple of them. So we will have a x1 and x2. Let's say have x1 and x2. We're going to take the linear combination and feed it back. So this is going to be the feedback root here times k. And this is going to be the input here. So it's a bit different than the p-type controller because this is the classical setup. You have the output. You're just feeding back the output, r minus y times k, which is basically the error here, tracking error. But instead of having that, we have basically this ABCD system, this differential equation, set of differential equations even, the state space model. The state space model has x1 and x2. We will basically calculate this linear combination. We will assign some weights to them and take their sum and feed it back to the input. It's still a feedback, but it's different. And you can see that for a second order system, for example, we will have k1 and k2. So basically we have two coefficients rather than having one. Whereas p-type controller uses just a single static gain. Here it's a vector, more of a vector. So let's try to design this one here. We have a formula for that. Fortunately, we don't have to go throughout the whole process. What we can do is we can use the Ackerman formula, which is something we will do. Ackerman formula, which does give us a nice formula, which looks like this. So this is basically a row vector with a bunch of zeros, and the last entry is going to be 1. And the size is basically the same size as C. So it's 1 by n. And then I've talked about this phi c. I've already defined it. It's the controllability matrix. And we will take the inverse of that. Therefore, it is important to be able to take the inverse of phi c. And then we have something called PDA, which is basically the desired polynomial. P desired S, which was basically S squared plus, which we called S squared plus 2 times zeta times omega n times S plus omega n squared. But it doesn't have to be a second order one. This is the second order version. Let me define a single one, which is S plus P. It could also be the combination of these or any other polynomial. So AS, so basically ANS to the power of n plus AN minus 1, S to the power of n minus 1, plus dot 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 plus S A2 S squared plus A1S plus A0. So an nth order polynomial could also be used. A specific first order polynomial or a second order polynomial can be used here. But of course, you have to choose the order that you are working with. So if the system is a second order one, you have to choose a second order polynomial because otherwise it doesn't make sense. But it is called PDA for a reason, because we will substitute the matrix A into this polynomial. So it's basically going to look like this. PDA here. And it would be A times A to zeta times A, and then omega n squared identity, basically, in this case. Or A plus P times identity, which is basically 1 and A is scalar. Or here, and it's going to be A to the power of n, A to the power of n minus 1, A to the power of 2, A to A, and then identity matrix. Why are we doing such an interesting thing? We're taking a polynomial, substituting the matrix A into it. Well, it's more about the Cayley-Hamilton theorem, and it's more about the fact that the matrix satisfies its own characteristic polynomial. So, and when we substitute A into the desired polynomial, what we are left is basically the gap between our polynomial and the desired polynomial, and it kind of uses that for that. So it has some theory behind it, and we're not really going to cover that here because it's too long and too mathematical. If you're interested in it, you can just look up the Ackerman formula and then the Cayley-Hamilton theorem. And in conjunction with these two, you would basically get your answer. But it takes quite some time to understand it and to cover it. And we're not going to really do that because the Ackerman formula is well established and we're going to use it here. So we're basically using the polynomial, the desired polynomial, substitute in the A matrix of our system under consideration. And that will give us basically a controller here. But I'm going to show you that this is basically the formula that we use, but we can also do it manually. But I highly suggest you to use the Ackerman formula. So basically, if we want to assign a certain pole to this, we are not going to be able to take the inverse of phi c because it doesn't exist, as you can see. So let me just try to come up with a PDS, which looks like S squared plus, or let me do it like this, S plus 2 times S plus 3. For some reason, I've chosen these two poles. Now, if I want to calculate PDA, what I have to do is I have to get the coefficients here. PDS, S, all, and then maybe convert them into double. And PDA is going to be coef 1 times A plus coef 2 times A plus coef 3 times identity matrix 2. The reason why I'm not using subs A is the fact that I can add matrices and scalars in Matlab. It's not the same. So this is not the same as adding the identity matrix here. These are different things because this one here is a dot plus operator, sort of. So it means that it is element-wise summation. So it adds 1 to each element, whereas this one here is identity, and if we use subs, it will mess up. You might try to subtract the constant term and then do some crazy stuff with that and add it back again as the true value or something like that. But yeah, I'm not going to bother with that. I'm just taking the coefficients and I'm just going to do it myself. So I know that coefficient 1 times s squared, coefficient 2 times s, plus coefficient 3 times identity should be the actual thing here. So when I try to run this, you can see if we didn't mess up stuff here. So let me just try it again. In line 24. Column 12. What? Oh, of course. Let me get rid of this. Yeah. So let us open this back. There we go. Now we can see that the matrix is singular. Therefore, it kind of messes up the whole process here. What we can do in order to cheat, which is not correct, but I'm going to cheat, I'm going to use the pseudo inverse, which is not the inverse, but it's kind of the projection inverse kind of a thing. And this is an engineering thing that I'm basically doing here. It's not mathematically correct, but I'm just getting over it. And you can see that we get a k vector, but unfortunately it is 0 and 0. Yeah. What is PDA actually? We have a PDA. What is the pseudo inverse of phi c? We still have that. But if we multiply PDA and phi c here, we kind of get a 0 row here. Since we are interested in the second row, it gives us 0 here. Yeah, quite sad actually. Let us try something else, but I guess this will not change the outcome here. We get a 0 vector here. So we're not quite lucky. We are not able to change anything at all for this system, which is quite sad. Now, of course, we have to note the fact that we cannot take the inverse. So this is still not possible. But we did come up with a better ABCD pair. And it was this one here. So if we repeat the step with this one, and opening up this one here. So we are updating basically these. Since this is a scalar one, let me just try to assign my pole at 3. And PDS is basically that. We have just one less of a coefficient. So coefficient 1 times A plus coefficient 2 times identity should be the right thing here. And it should be basically 1 times inverse, and let's see what's going to happen. Phi c should also be updated, by the way, because we have a scalar one. This is going to be b. PDA is this one here. Phi c is this one here. Yeah, why don't we get what we want? PDA. We updated A and B. What is the issue here? So now it says the right thing, but am I missing something here? So this is basically the part. We get the denominator. We couldn't assign stuff here. But then I'm redefining A, B, C, D. For some reason, it doesn't work then. All right. Then we have PDS. Then we have coef 1 and 3. Then we have, oh, this is not a, yeah, no, I've seen it. This is basically not existent here because it's scalar. PDA 3 and then phi C. Actually, I can just run it. Now it will work. K being 1.5. So, yeah, this is the scalar basically formula for the Ackerman formula here. And we came up with a controller which is 1.5, which oddly resembles the fact that we had pole divide by 2 strategy here. So the pole was 3 and the coefficient is 1.5. It's kind of the same thing here now. I can, of course, change this fact by just updating my model. And you'll see that if I run it, if I look at K, now it's the pole itself. So it's basically depending on the model itself, but we can see that it is basically 3 here. And the assignment is done via this one here. So, and since you have this model, what you can do is you can just convert it into a transfer function. And using u equals kx is going to be something special. And we'll see what that is going to be. So we have talked about a special case of the state space model here. We have seen that we can design a p-type controller. And in the scalar version here, the p-type controller is the same as having a state space, a state feedback controller. So they're basically the same if we're talking about a scalar system. If it's an nth order system, then the state feedback controller is kind of the generalization of a p-type controller. So let's have a system that can actually work in a signal order as a signal order transfer function. And then let's design a p-type controller. Let's design a state feedback controller. And then we're going to talk about another topic and then conclude our day. So what happens if we have a transfer function instead of having an ABCD matrix here? We kind of have covered it, but I'm just going to talk about a more detailed conversion here. So this is going to be basically our transfer function here. 6 times s plus 12 divided by s squared plus 0.2s plus 101. There we go. If we have a transfer function like this, and if we want to convert it into a state space representation, what we're going to do is we're going to basically discard the numerator part. We're just going to focus on this one here. And we're kind of going to define a transfer function that has numerator 1. So instead of converting this transfer function into state space, we're just going to take the characteristic equation and the numerator equals 1. So 1 divided by the characteristic equation and focus on this transfer function. Once we've converted this one here, it is going to be fairly easy to convert the actual transfer function into state space. So why am I doing this? Well, because it is going to be a transfer function between the states that I'm going to define and the input. So if you cross multiply everything, you'll see that it will be basically looking like this. And s squared times x, so let me just work my way out, x, x, and x. So there we go. So, and remember that the initial conditions are 0. So if I have s squared times x, it means that the second derivative of x, and this is going to be the first derivative here, and that's just going to be itself. So now I have the differential equation. Now it's easy to convert the differential equation because I always start with x1 equals x, I take the derivative of x1, which is x derivative, which is going to be x2. And then x2 derivative is just going to be x double derivative. And I stop here because the highest order term is x, the second derivative of x. So therefore, I'm just going to use this. Now you can see that the first equation that I come up with is basically this one here. x1 derivative is equal to x2. Then I'm going to use the actual differential equation here and move them to the right. So that's going to be minus, that's going to be minus here. And of course, let me move this one to the end, plus u. Now I have some definitions here, line 11, 12, and 13. So I'm going to substitute them. So instead of having x double derivative, let's have x derivative, x2 derivative. Instead of having x derivative, I'm going to use x2. Instead of having x, which is basically x1, I'm going to have x1. So I'm basically getting rid of all the x terms, and I substitute them as x1, x2, x3, whatever. Now rearranging them a little bit more would help out. Let's move this one here. And well, we can actually write down our A matrix now by just looking at these two lines. You can see it is basically 0 times x1, 0 times x1 plus x2 plus 0 times u. There we go. Therefore, I can say 0, 1, and the next line is minus 1.01, and then minus 0.2. And the B matrix here is going to be, the first one has 0 u's in it, the second one has 1. So this is basically the notation here, the A matrix and B vector, basically. And all that I've done is I've just I did get rid of the numerator part. I replaced it with a 1, and I took the denominator. Then I've cross-multiplied everything. Then I did just convert the Laplace notation into derivatives. I then ended up with the differential equation. Then I defined x1 equals x, started taking derivatives and defining new variables for each derivative. I stopped at the highest order term. Then I took the necessary relations between x1 and x2, and then I also used the differential equation itself, replaced the variables, and then I just converted into matrix notation. Now, we did come up with 1 divided by, actually we have x divided by u covered now. What is basically the static equation that we have? C times x plus du. So that's the static equation. So the first part was about the dynamic equation, and the dynamic equation is just about the characteristic polynomial. So therefore, I'm just focusing on that part. I created a state transfer function, basically. Now, if I divide the line 21, the output equation or the static equation into u, each term dividing into u, you can see that the expression comes quite easy to handle. Because I have now the x divided by u part, what I need to do is I need to come up with C and D matrices, and then my transfer function will be complete. Now, I can see that this portion here, which is the transfer function itself, y divided by u equals this, is basically consisting of this times 1 divided by this. That was the reason why I just defined a numerator 1, and I focused on the characteristic polynomial here, because this is going to be x divided by u. So if I multiply everything with u, you can see I have this new equation, which is the output equation. Let's basically expand this into this one here. We can see s times x is going to be x derivative, and then I know that x derivative is basically, you can look it up, x derivative here is x2 here. So this is x2, and x was x1. If I move x1 to the front, you can see that this is basically plus 0u, 0 times u. Therefore, I can state the C matrix here, 12,6, and D is going to be 0. That's it. So these are basically the steps that I carry out. I just take the characteristic polynomial, get rid of the numerator, put in 1, cross-multiply them, convert it into a differential equation, define each new derivative as a new variable, convert it into a state space dynamic equation, basically get A and B. Once I'm done with that, I just look at the numerator part, multiply that with x basically in this case, and then convert it into the static equation or output equation, and I've acquired basically the necessary matrices. Now, once you're done with this, what you can basically do is you can just go ahead and get rid of everything here, except A, of course, like this. Define it as SS, A, B, C, and D, and then convert it into TF. There we go. I see the output of this line 11, 6s plus 12 divided by s squared plus 0.2s plus 101. So we have basically converted this transfer function into state space representation. Now let's design a p-type controller and also design a state feedback controller. So let's start with the state feedback controller. Now we have A, B, C, D. All of that I'm going to do is first, I'm going to look at the controllability matrix, which is going to be B and A times B, because it's a second order one. If the order continues, you're going to continue multiplying with A basically. So the general version here is A to the power of n minus 1 times B. Yeah, n being the order of the system. Since n is 2, the maximum term is A, so we stop at A times B. Now, if the inverse of phi c, so if I'm going to be able to take the inverse of this, which I can, it seems like the system is controllable. Once it is controllable, I'm going to define the Ackerman formula here, 0,1 times the inverse of phi c times PDA. This should give me basically the state feedback controller that I'm looking for. So before I do that, let me just take this here, or actually this one here. And for some reason, I'm just choosing 20 and 3. I have no special reason to choose these. And I'm going to basically look for K. So what is K? K is this one here. So what happens if we have the state feedback controller? What now? So X equals A times X plus B times U, Y equals C times X plus D times U. So now what we do is we just say that the state feedback controller is used like this, U equals minus KX. So that's basically the relation here. Sometimes the minus sign is there, sometimes it's not. As far as I remember, we should have a minus sign here when we use the Ackerman formula like this. Now, we can go ahead and substitute this. We can see that instead of having U, we will have minus kx, because that's the substitution that we have. And when we do that, we see that the system changes into the following here. A minus bk times x. And the same goes for this one here. So c minus d times kx. And the system becomes an autonomous system. And this is basically the closed loop A matrix. This is basically A closed loop here. And we have C closed loop here. And there we go. Now, when we're looking at a state space system, how can we determine what its poles are, or if it's a stable one or not? Well, it goes back to basically x dot equals ax plus bu. If you only have this one here, and y equals cx plus du, d times u. When you look at c times s minus si minus a times b, so inverse times b plus d, this term here, si minus a inverse, is going to have basically a determinant of si minus a somewhere. So 1 divided by that times the cofactors, cominors, and all that stuff that is necessary to calculate the inverse of a matrix. But all those terms will appear like a matrix. Then we will multiply everything and sum everything or add everything together, and it will basically end up being a polynomial here, which will represent the numerator. But the denominator will come from this term here, 1 divided by that si minus a. And this determinant si minus a is a special thing because it's going to be the characteristic polynomial or the denominator of the system. And also, s here is going to be the eigenvalue of a. So, yeah, we can just test it by looking at the determinant si minus a, which I'm going to do in a minute. But you can see that that si minus a problem here is an eigenvalue problem, and it means that the eigenvalues of a are going to be s here, or the solution to the polynomial here. So, or this equation is satisfied when we have the eigenvalues for s. You can just view it from different perspectives here. So let's actually do this for once. Let me just get rid of this. Let me comment this out. So I'm just going to look at the determinant s times identity matrix minus a. And it should resemble something where the transfer function looks like this. So you can see the determinant si minus a gives us s squared plus s divided by 5 plus 101 divided by 100. So this is basically the characteristic polynomial. So if you calculate this, you can just get a polynomial here. Now I'm going to do something else before I go on. I'm going to define two parameters which are going to be real parameters. And I know that the closed loop system looks like this, a minus bk. And if I look at the determinant si minus a minus bk, then I should get basically the closed loop characteristic polynomial. This is something you know from the past. You know what PCS is. K1 and K2 are going to be controller parameters, but I'm basically looking at the closed loop transfer function denominator here, and it will give me basically the following: s squared plus k1 times s minus k2 times s divided by 5. Now, what I can do in order to trick stuff here, I can just solve it with usual stuff. That is being using the coeffs method here. Let's get the coefficients of S, PCS. Let's equate it to the coefficients of PDS. Let's solve the problem. Let's look at the solution here. Not run 1, I'm sorry, run 2. Probably we have some extra coefficient here. So PDS, PCS. No, we shouldn't have. Oh, it's in the S term, which it shouldn't be. It's B. Why do we have this problem now? It's I minus A minus. Oh, there's a multiplication minus sign, which is weird. So let's try it again. Now we go sol.k1, sol.k2. So basically what I can do is I can just come up with k, let's call it k val, and convert it into a double. Let's have sol.k1, sol.k2. So run to, there we go. And what is k? If we don't override it, that's going to be k. So let's see. Now you can see the interesting thing here is that we can actually solve this without using the Ackerman formula. We have just basically assumed k as a vector of k1 and k2, which are not known. And we've used the fact that this is basically the characteristic polynomial. I can also change this a little bit more. What I can do is I can just come up with a closed loop system here, which is going to be calculated by C times, or CC times. Now I need to use the closed loop stuff here. So S times identity 2 minus AC times, or the inverse of that. So let's have basically inverse here. Inverse of SI minus A times BC plus DC. So let us actually define AC. AC is going to be the closed loop A matrix is going to be A minus BK. And BC is going to be B. CC is going to be C minus DK. These are not really that important, by the way. And DC is going to be D here. Once that's done, we are actually almost there. Now what we need to do is we need to get the numerator and denominator, or PZS and PCS, use num then, maybe simplify stuff, even fraction, TSS, simplify, there we go. Then I don't really have to do this. So let's run it again. And we messed up stuff. So PCS, yeah. Then we have to basically use something like pol equals coefs of PCS as all, and then normalize pol with coef 1 or pol 1. Then use pol for the left hand side because we have 100 as the highest term here. Now again, you can see I have basically solved the same problem. Now I also have PZS and PCS, so I can see what the closed loop looks like. And yeah, that's quite interesting to note here. When you know the closed loop symbolic state space model, sort of, you can use the symbolic toolbox in order to come up with a transfer function, and then again use the polynomial coefficients assignment method that we use as the algebraic method all along. But of course, this doesn't make sense if you're in an exam or if you're using a pen and paper, because this will become more complicated, whereas you just need to have some linear combination of the A matrix here and the inverse of a certain matrix. Then you multiply everything and you get to K way faster and way easier than this way here. But I wanted to point out and show you that these are basically the same. It's just the problem and the nature that changes. But other than that, this is just the closed loop state space representation. You can come up with the closed loop transfer function. This is a longer route, as you can see. You can just also look for determinant Si minus A minus BK, and then you have the characteristic polynomial, take the coefficients, equate it to PDS, and solve it. So the Ackerman formula basically solves this for us way easier and way faster. Now, yeah, so here, instead of having, of course, this, what I did, I just added a reference to this. So I'm having a minus kx term here, and I add a reference to it. When I do this, I get basically the plus b times r and plus d times r terms here, where I can at least apply an input to the system here. So we can also basically define the closed loop here. Once we have defined our, once we came up with the controller, we can just look at the closed loop here. So you're just going to write it like A minus BK is going to be the A matrix, B is not going to change, C minus D times K is going to be the C matrix, D is not going to change, and then you might also want to apply some step to it. So that's also possible. Let me comment this out. Hope that Matlab is going to give it. So let me actually also plot the system. Do we have it here? Nope. So maybe we want to convert it into this one too here. So TF maybe. So let's have TS black and then TS in red for some reason. So yeah, other than being not able to see it quite good, yeah, we should maybe have them side by side. So now we have them side by side. And what does this mean? Well, we had a open loop transfer function that looked like this. And we designed a state feedback controller that changed the system to the following, which I don't know why it is chosen or why we have this. We can just basically change the poles here to have a certain thing. For example, what we can do is we can maybe assign some zeta and omega in values to have a better understanding here. So let's have zeta equals 0.59, which was roughly 10% overshoot, I guess, something like this. Let's have omega n equal to 4 divided by TS times zeta here. And let's have TS equals 1. So I'm just choosing them. Then let's define S squared plus 2 times zeta times omega n times S plus omega n squared. And let's run it again. So this is basically the result here, but I guess we should change the title, or we should at least look at the step info here to be sure. There we go. So we can see the settling time is 1. The overshoot does not really work, but we can see the settling time is at least 1. Why did the settling time work, but the overshoot did not? Well, it lies on the fact that we should look at the 0 pole location here. You can see we have a dominant 0, and the real part of the poles is basically at 4. So that's kind of the issue here. Let me maybe just change this into the following. Let's have 1. Let's have PZ map of GS on the next one here. And then let's have 3 here. And then 4, and then PZ map. TS, and then 4. Maybe that's going to help us out a little bit more. There we go. Now we have poles and zeros here. We can see our pole pair is at -4 and probably at the exact zeta value that we're looking for, but we have a 0 that's dominant, so this is basically messing up stuff here, whereas our poles were here. So I want to show you the following. What if we are going to design a p-type controller for this and try to assign the same stuff that we had before? So we have basically zeta and omega n. Let's have sims k, kp, call it real. Let's have tss, kp times gss, and divide it into +1. Let's have pzs, pcs, nom-den, and let's get coefficients of PCS as all. We should still have PDS here, so that's still there. So let's define a problem. Coefs PDS, comma S, comma all should be equal to pole, and sol should be equal to solve the problem. And let's have sol here. So you can see we couldn't solve it. And what could be the reason there? Let's see. For I equals 1 to length problem here. I'm going to display VPA, problem I, comma 4, and end. Now we can see that we still have a normalization issue here. So pole equals pole divided by pole 1. Let's solve that. Now, do we have a solution? We don't. What could be the reason here? Well, the first equation is satisfied, but then here, the last two equations cannot be satisfied unless they are aligned with each other. So this equation should be somehow the same equation as this one here in order to have a unique KP and satisfy both equations. So we cannot use 6 KP plus 0.2 to solve it to equal to 8, because it would then be 8 minus 0.2 and the answer divided by 6, I guess, which is 1.3. But 1.3 times 12 plus 101 doesn't add up to 45.78. So they kind of prevent us from having the solution. Whereas the state feedback controller in this case has a solution for it. And we've seen that actually what the reason behind that might be, because we have two coefficients and because they appear in a certain place. So I'm just going to do the stuff here and just show PZS. I'm not really interested in the whole solution. I just want to see what the problem looks like. Oh, actually, maybe here. So let me copy this part here, and let me put it here. I'm looking at the problem. So now the first problem is a p-type controller problem, and we can see we cannot assign it. But for the PD type, actually for the state feedback type controller, what we have is we have two unknowns and two equations. So there's a unique solution here. So, and the equivalent of this is basically the following. We can get the same result by trying to basically design another controller. KP is not enough, so let's opt for a PD controller. And for that, we need FSS, of course, and then, or it could also be a PI controller. FSS is KD times S plus KP. So that could be the case. Now, yeah, that should help us out here. Let's see. Let's run it again. Now, of course, due to the normalization, it looks a little bit weird, but we see that we have KP and KD as values, and we sort of end up having two parameters and two equations and a unique solution. It could be even a better case where we have the PD controller in the feedback loop. So maybe that's even solving it more accurately. Well, it doesn't really change this part here, but at least it doesn't add a 0 to the system. But you can see and kind of talk about the fact that the state feedback controller is a sort of a PD controller. And I have another proof for that. And the proof would be the following. If we examine, let me just get rid of the PD controller here, like this. Let me get rid of this portion here. And if I run it, I get this one here. So when I look at the equation where I have K1, so minus K1, basically, times X1 minus K2 X2 plus R. This is kind of my equation here, because this is the state feedback law here. Now, I know that that's roughly 44, and I know that this is 7.8, or I can also stay like this. So when we were converting stuff, we defined basically x1 equals x, and then x1 derivative was x derivative, and that was called x2, and we stopped there. Now you can see that here, actually, and y is equal to x in our case. Now, for the case where y is equal to x, that's not mandatory here. So let me just get rid of it. So when we have x1, what we have is we have actually x here. When we have x2, that's actually equal to x1 derivative or x derivative here. So you can kind of see that this kind of part is about the proportional part. It has Kp here because it just takes the state itself. And here we have the derivative of the state. So we're basically having a p proportional part and the derivative part and the combination of that, which kind of resembles the PD controller. The only issue would be the following, where we have y equals cx plus du. And we know that we have this 12 and 6 here. So our output would look like 12 times x1 plus 6 times x2. So this is not quite the PD controller that we are going to design when we choose the PD controller, but they are equivalent in the sense that they have a derivative part, a proportional part. We combine them and feed them back. But it's not going to be the exact same coefficients because the output is not generated like that. If we would have the output equation like y is equal to x1, then stuff changes. Then what we can see when that's the case, if this is the case, or let me also have C in it. So c times x1 here, or actually x here. What I can get is I can basically write down the other one, the classical PD controller, for example, kd times s plus kp times e, as you all know. So I'm kind of trying to show you what the actual feedback mechanism is here, or what the essential difference is. We have r minus y here, and yeah, if we distribute this whole thing here, this would be times r, and then minus y times this one here. So that's what we have basically. Now, this would become minus kd times y derivative, and then minus kp times y here. And then we would have a stuff that looks like kds plus kp. Whereas if y is equal to cx, let's say cx1, or let's have just a coefficient c times x, then yeah, this should be scalar in the scalar sense. Then we would somehow something like y and then y derivative. But you can see it's not quite the same, because from this feedback it should be cx, c times x, and then this should be c times x derivative, where we have kd times c and kp times c. So it's never going to be the exact same. But you can see that for a second order transfer function, when we are designing a state feedback controller, what we at least can say that it has a PD effect. It could be viewed as a PD controller. But if it's the third order one, then due to the rule, it would look like this. U equals minus k1 times x minus k2 times x derivative minus k3 times x double derivative. So it doesn't really go through that pattern, but if you think about it, it kind of is using all the states, and if y is equal to x, then you can see it's the output, the derivative of the output, and the second derivative of the output. So, but the important part here is that for the state feedback controller, you will always have equal amount of unknowns and equations. So you will always have a unique solution if the system is controllable. If you can take this inverse, you can, if you take the inverse in the Ackerman formula, which we didn't use now, where is it? There we go. If you have this inverse, if phi c is a full rank, if it's not singular, etc., then you will always have a controller. When you have a controller, you will have a unique solution here. Because we have n coefficients and the system is a n by n system, we always end up in a unique solution for that. So this brings up the following. When we are designing a p-type controller like here, then we are basically depending on the root locus here. So we're tied up to the root locus plot. When we have the PD controller, the root locus can be banded so that each point can be accessible on the root locus. So that's another story. But for the p-type controller, we have to design a we have to look for the root locus, and if it's on the root locus, then we can design it. If not, then not. So what we can do is we can look at the root locus of our GS transfer function here, for example, and then choose a specific point here. So let me choose a point here. So minus 4.15 seems like it. So instead of having this, I could have zeta equals 1, omega n equals 4.15, I guess. And oh, we still don't have the solution. Is it a numerical thing here? Why don't we have the solution here? Am I missing the point here? 4.15. And the gain is going to be 135. Yeah, this should be it. PDS looks like this. Coef, what is solve? PDS equals 0, gonna give us. What is this in double? 4.15. So it is exactly 4.15, but our p-type controller for some reason doesn't want to play with us. I don't know. The gain should be 1.35. So why am I not seeing it? KP plus 1, PCS, normalize that, solve it, and it's not able to solve it. So empty. It doesn't make sense actually. Why am I not able to solve it? Probably it's not 4.15 exactly, and maybe this part here is bothering it. I don't know. Interesting. So what happens if I have feedback 1.35 TS, 1 ZPK it seems like it's not exactly on top of that. So maybe no, it's not something nice. $34. Roots of that. 1, 8.24, 17.09. Yeah. What is the absolute value of this? What is 4.12 divided by the answer here? 0.9966. The absolute value is 4.134. So let's use these specific values. Hopefully it will work. So 4.134 and 0.9966. Still not accomplishing it, I guess. Yeah, it's not playing with us. Yeah, let me just choose this as PDS. Don't bother with that. Numerical stuff matters because, yeah, numerical precision. Let's have multiplication here. So instead of having that, I'm just going to replace it with this. And I'm using the same PDS, I assume, here. Yeah, there we go. So hope that this time finally we could have come up with the controller. 67.50. So double sol. That was a pain. So now 1.34 is basically the gain here. And this is basically our state feedback controller. Now there is a resemblance here, and we will see it when we have C here. it's 12 and 6. And what happens if I multiply this, the p-type controller value, Kp, which was 1.34 times C, you can see this is basically K1 and K2 here. So we can conclude the following. The root locus changes its meaning, or we can change the meaning of the root locus now. We can say that if the state feedback matrix K1, K2, so K1 and K2, if this is aligned with the output matrix C, then there's a p-type controller that we can basically design using the Ackerman formula or using basically the conventional methods like root locus. If I can align this, I can do this with one parameter because there will be certain coefficients. So it would be Kp times C. And of course, Kp times, so K1 would be equal to Kp times C1, and K2 would be C2 basically. But if it's not aligned with C, if I cannot do this, then I cannot assign it. Then it's not on the root locus. So the state feedback is kind of a new perspective that we gained now, and then that we can use in order to conclude stuff about closed loops now. And we also can conclude the following. State feedback controller can freely assign any combination of poles to a system in the closed loop, which means that we don't actually have the restriction of the root locus because it's not a p-type controller, it's a state feedback controller, a more generalized version. But the problem there is to have these states available to you. You need all the states that are defined in your mathematical models in real life, and you need to measure them all. You need sensors, basically. Then you're going to take the linear combination of them and feed it back. Then your system can behave as you wish. You can choose all the poles that you want, and you have no restriction at all. That seems nice, but it is not. Which brings us to the next and last topic of today, which is the observer. Now, when we are designing state feedback controllers, we're basically dealing with a full assignment problem, which means that we have coefficients in all the S terms in the closed loop, so that when we choose a PDS, we can directly assign it without having to deal with dominant pole placement at all. So state feedback or state space is basically the solution or the anti to dominant pole placement. Because we use full assignment. So what I mean by this is the following. Assignment. I mean the following. I can assign all the poles anywhere I want on the S domain because I'm using n coefficients in the K vector here. K is a vector. I have all the necessary stuff, the structure. I measure everything. I have the linear combination as the control law, and I can assign everything. I can decide on each pole of the closed loop freely, which is quite powerful because the dominant pole placement is needed because of the fact that we cannot really assign everything freely. If I push or if I choose two poles here, everything else should be pushed away because my modeling is too basic, or I'm not able to push everything away. So I'm treating it like a low order system. But here I have full control. This is partial assignment, basically. I have some poles that I can assign, or a region where I can assign poles, or I have a special setup that I can come up with certain coefficients, and that's it. But here we don't have that problem. We just can get the full assignment. We can change everything as we wish. Of course, this raises other questions. How should I assign poles and etc.? But from here, you go to LQR, MPC, and stuff like that, because these kind of try to answer the choice of K, because, yeah, we are just looking at the full assignment problem here. We don't deal with LQR, MPC. These are advanced topics from here on. Now, yeah. Another restriction here is this comes at a price. The full assignment here comes at a price, which is measurements. Now, sometimes we are not able to measure stuff physically, maybe a Hall sensor is needed, maybe it's too expensive, maybe sometimes we don't really want to measure it, or it's quite difficult to measure. Then we need an assistance here, another thing that can help us out, because when we have a fifth order system, then we need 5 coefficients and 5 measurements. So K1, K2, K3, K4, K5, they will be multiplied with X1, X2, X3, X4, and X5, and we are going to combine them. So that's not an easy task if you think about it. We need 5 things to measure, whereas the PID controller, for example, measures the output, and yeah, that's basically it. Here we have too many measurements, but there's a solution to this, a kind of a solution. We can come up with a structure that is called an observer. And the design of an observer is the easiest part. The difficult part is to understand the observer, because we are going to use the Ackerman formula as we used it for the state feedback controller in the observer design. That's no big deal. The actual problem is to understand what it does and how it does it, basically. So let me first design an observer for this. So let's have the system here, this one here. There we go. Now, when we're designing a controller, let me also take that part maybe, in order to be able to compare that stuff. All that we need is we need a desired polynomial, we need phi c, and this kind of thing here. So we need phi c. This is basically the controller. We use Ackerman. We need sims s here, and a certain PDS, coefficients, PDA, and it's designed. So this is K. Nice. Now, let's talk about the observer. I'm going to show you what the observer is. It's basically the following. D times U, that's it. So since we are dealing with a linear time invariant transfer function, what we can do is we can go ahead and copy the system. Since we are copying the differential equation, it should be basically the same behavior. It should behave like the system. So I can calculate the stuff by using the same set of equations, and that should be it. The issue here, or the issue that the observer is solving, is basically the initial conditions, because since the system is linear, it will behave linear, and it's not a big deal if x0 is equal to 0. You don't really have to measure it. You can just calculate it by copying the system model, and you can use this as the reference system, and that's basically it. Nowadays, since we have digital computing and digital signal boards and stuff, we can basically use this, apply this into the real world digitally. You can just have the difference equation, have a computer that calculates all the states for you. You don't really have to measure it. But the issue here is that it might have an initial condition, or some disturbance might act on it. So then stuff changes, or the system model is not really represented well by the model. The actual system behaves differently. It's a nonlinear system. There are some assumptions, heat, pressure change, noise. All this needs to be also taken into account. Then stuff changes a little bit. Then you're not good to go when you're just copying the system here. And by copying, I literally mean copying, because we will have a sort of a duplicate state, duplicate output. We've just basically copied it literally. Now, the solution to this is to basically use the feedback again. Even though we're trying to estimate the states of the system or kind of trying to predict stuff, we're again looking and comparing to these two outputs here. We are still measuring the output of the system, or we are going to still measure the output of the system, and we have our own output. If there's a certain difference, then we are going to feed this back. So what we can do is we can just adjust our state estimates, and that's basically the point here, by taking the difference between the actual output and our estimated output. Now, these underscores are basically estimated stuff. So I have the same differential equation, I have another differential equation, but I act on my differential equation based on the difference of the outputs of both the actual system and my estimate. Now, of course, you cannot go ahead and choose any L here and then assume that this should work. This is just too theoretic and it looks too nice. But what you can do is you can define something that is important for us, namely the difference between the state and our state estimate. And we can, again, do some crazy stuff here. We can take the derivative, for example, that will end up in the difference of the derivatives here. Now, this equation here, and we're kind of going through a proof here, the x dot here is defined as the right-hand side here. So let me get rid of the terms here. So we have this portion here minus this portion here. So it's kind of a difference between the dynamics that we have here. There we go. Now what we can do is we can do this basically minus that, and there we go. Now this might seem silly, but the end result is interesting. We defined an error, we defined the derivative of it, and we're looking at the derivative terms. And luckily, the inputs vanish because they are the same. These don't contribute to the dynamic parts or to the dynamic error here because they are the same. So then we end up in seeing y. We can substitute y equals cx plus du. And then we can take this part too and substitute it also instead of y underscore or estimate. Of course, this is a minus sign. So then you can see the du terms also vanish here. Plus du minus du, they're gone. And we have a common term c. And there we go. Now there's also a common term here, which is basically a. This one is gone. This one is gone. And there we go. And we still can combine stuff here. So a minus LC is basically this term here. Now we know what x minus x underscore is because we started with that, and we define it as the error here. So we are going to substitute that. Now we have an autonomous system. That is the beauty of the observer, and this observer is called Luenberger observer. Now we can state the following. If A minus LC is a stable or is Hurwitz stable, it's basically stable. If this is a stable matrix, or if the eigenvalues are on the left half plane, then ST tends to infinity, limit of ET will tend to 0. Why? Because this is an autonomous system, and this is a stable transfer function. At the end result, due to the definition of stability, E will tend to 0. So this is quite powerful, because if E tends to 0, it means that this difference will tend to 0. And it means that our estimates will tend to the actual states, because there will be no difference anymore. So we need to choose this gain L, or matrix L, in such a way that A minus LC is going to be stable. If that's the case, then the error dynamics, or the difference between two linear systems that kind of have the same dynamics because we have copied it, they should basically, or our estimates should basically give us the actual system states. And that is observing the states of a linear time invariant system. So we can use a certain transfer function, because this is a transfer function, although it seems like a state space model. And we can build a system and come up with L, and we're good to go. If A minus LC is stable, then we have a system that can predict what the states of the system is. Then we can change our strategy. Then we can do K times X. Instead of doing that, we can use K X underscore. Since X underscore will be something digital and that we've basically constructed, we don't really need to measure all the states. The only measurement needed here is basically the output, because we're using the output as the measurement, the only measurement here. So this line 19 and 20, these equations here, or this system here, which is a copy system, is the Luenberger observer. And this observer should give us basically the estimates of the states, which we are going to basically use for state feedback. Now, then we have basically a state feedback controller with the Luenberger observer together, that uses Y and creates basically our control signal here. So then we have the actual system, maybe like this, and the connection is changed like this one here. So this is basically it. We use the Luenberger observer, we get the states, give the states to the state feedback controller, we have created our control signal applied to the system. Now, the order of our controller, of course, is not low. So this is not only being a static vector anymore, because we have the copy of the system. So this is kind of GS plus some extra feedback. And that would mean that the order of our Luenberger observer is going to be n. And our controller is then also going to be an nth order controller. So it's a high order controller now. Why? Because it has the model of the system. Now we are at a point where we have kind of the model matching equivalence here, because we have kind of GS in our control structure. Or we could also call this like the Smith predictor equivalent here, because it still relies on the system model. Or it's also called internal model control, because all these methods basically use the system model here. We are relying on the system model. But of course, it's important to note that the Luenberger observer is quite powerful, and it's basically in some way the Kalman filter here without the statistics. If you add some statistics to it, if you have the extra stuff that is necessary, or the update law and stuff, this is basically a very simple Kalman filter in this case. So we're basically using this for state estimation at this point. Yeah, so this is the whole theory behind that. And all we need to do is we need to come up with a stable L, or stabilizing L for A minus LC. And the interesting part about that is we can basically use the same stuff that we've used so far. So here, A minus B times K was basically Hurwitz stable, because this was basically the closed loop autonomous system matrix here. And if the eigenvalues of this is on the left half plane, then we're good to go. The only difference here is that the unknowns in terms of structure are not on the same spot. So L is here, but K is here. And C is basically a row matrix, B is a column matrix or vector. Yeah, but this doesn't prevent anything from being possible, Because we can do the following. There is a rule that we can utilize here, and that's basically taking the transpose here, or in Matlab notation, taking the transpose like this. Why is this important? So if you have a matrix A equals 1, 2, minus 3, minus 4, for example, the eigenvalues of A and A transpose are the same. This is important because when we do this, when we take the transpose, we will end up in A transpose minus K transpose times B transpose. So this is going to be the same here. This means that we will end up in the same structure here. So you can see the resemblance here. A is a square matrix, A transpose is still a square matrix. L is unknown, K transpose is unknown. C is a row vector. B is a column vector, but its transpose is a row vector. So when we are using the Ackerman formula, what we're going to do is, instead of using A, we will use A transpose. Instead of using K, we will use K transpose. Instead of B, we will use B transpose. Because at the end of the day, we're considering basically the observer here. And that's also the reason why we call it the dual, because we kind of take the transpose and we have the same result. So the design will be this one here. Instead of using B, I'm going to use C transpose. Instead of A transpose. Instead of B, C transpose. Now, let's assume we just take 20 and 20 for some reason, I don't know. And then we do the same, but with A transpose. And here we have that. We have phi C and then PDA, but we will take the results transpose here. So let's call this L. And yeah, let's see what happens. We're missing the multiplication operator somewhere. So maybe I should do something like that. Nope, still an issue here. So am I able to define this? Well, it doesn't know what C is. Line 51. Where am I actually? Run 3. Why am I running that? Run 3. So L, we're going to take the transpose. So L is going to be L transpose. So, and why did we do that? Well, let's look at A minus LC. Of course, we should maybe call it capital L. And the eigenvalue of that. There we go. We have the eigenvalues at minus 20. Instead of designing an observer, we kind of took all the transposes here, treated like a control problem, like a state feedback controller, solved it, and then took the transpose. Because all that we need to do is we're kind of looking for a polynomial, or the determinant of Si minus A minus LC. And this should be basically a certain polynomial here. Of course, since we're predicting the states of the system, and since this observer will serve like the state estimator, and then the state feedback controller will be connected with this, what we need to do basically is, if we, for example, choose S plus 3 and then S plus 4, let's assume this is basically our setup for some reason, then we need to look at the settling time, or we could do basically a certain dominance factor here, because when we are using the observer, it takes quite some time to estimate those states. And during this interval, time interval, we're basically feeding back false information. or we don't have actually the states, because it will take some time to tend to 0 for the error, which is being the difference between the states. So it is always a rule of thumb to design a observer or the observer faster, with faster dynamics than the control loop. So you should look at the control loop, the desired polynomial of the controller, state feedback controller here, and maybe 5 times, maybe 10 times further is a good thing to assign the poles at. For example, if this is 4, we can just use 40, and by doing this, we kind of ensure that the observer is way faster than the control loop, because they're more on the left than the system poles. So it should be basically faster than the control loop here. So we can look at A minus B times K and A minus LC here. And C, for example, the poles of the controller are at -3, -4, whereas we have assigned them the observer poles at -40, -40. Now, you can also do the following. There's also an Ackerman formula for the dual, which is based on this transpose here. If you take this transpose, what you can do is you can come up with the observer version here, which looks like PDA times inverse of phi O observability matrix. Then you have 0 and then 1. This is kind of the equivalent here. And if you look at that, that would basically, this is basically the same as C and then C times A. This is the observability matrix here. And you can use that basically. And PDA is just the same, but you just substitute A instead of that. And you can use this formula, but I don't really like to memorize this. So what I do is I skip that. I just take the transposes and use the controller version here. But you should know what the observability matrix is. And again, not all systems are observable. To be able to work, the system should be observable. So all the states of a system should have some influence in the output or derivatives of the output, so that we can basically gain back the information. If the state on its own is there and it has no effect on the output, it doesn't influence the output, how am I going to adjust the states that is not influencing the output by comparing the outputs of two systems, which is one of them is the original system and the other one is basically the observer here. So they should influence the output, therefore they should be observable, therefore the observability matrix should be invertible, which reflects basically the same thing as it was the case in the state feedback controller being controllable. When a system is controllable and observable simultaneously, we call that system a minimal system. And when you use min realization, you're basically getting rid of the not observable or not controllable parts of the system. If this is possible, you get basically the minimum realization, which is basically observable and controllable at the same time. So we have these states. I'm going to do one more thing, and I'm going to conclude this lesson today, which is going to test this out. So let us look at the dynamics of our system. So this is basically the dynamic of our system. Then we will have Cx plus D times U. And we also have a copy of this, X underscore here, Y underscore, C times X underscore, and yeah, maybe U underscore, but the input is basically the same. And let's review our things. We have basically a adjustment here, which was plus L times Y minus Y underscore. And then we have our control law, which hopefully is going to be minus K times X underscore. So if we use all these equations, if we combine them into one, what we will see is going to be the following. I'm going to eliminate these output vectors first. Let me just take this state vector here and this one here, state equation here. And this is c times x, and then this will be c times x underscore, where c can be factored out. So this is going to be L times C times X, and this is going to be minus LCX underscore. So that's one thing. Then we need Q U is equal to minus KX. Let's have also plus R, so that I'm going to have a certain input here. Minus KX plus R, let's plug it in. So this is minus BK X minus plus BR, I guess. Yep. So that's one thing. And the same goes for basically here. So we'll have minus KX plus R like this. So it will be minus BKX and plus BR. So we have some common terms here. So let's have a minus bk times that, where we also have a minus lc here for x underscore. So let's have that, minus lc. Let's move this a little bit more to the left. So that's it. Yeah, that should be basically it. Now, what is y? If we look at it, it should be cx plus du, where u is again this one here, which means that we will have minus dkx plus dr, and that should be it, I guess. So I've done this whole thing in order to be able to simulate this like a single system here. And I'm going to do that by defining basically an augmented system here, which will have states like this, the system states and the observer states. So when this is basically my new X augmented or closed loop, basically, my AA matrix is going to be the following. We will have A and minus B times K. So A times X, as you can see here, without derivatives, of course. So A times X, so this is X, so this is A, and minus BK times X underscore. And the next row is basically L times C, comma, I always do this, A minus BK minus LC X underscore. So this is A matrix. B A matrix is going to be B and B, probably. And CA is going to be C, comma, minus D times K. And then DA is going to be D. So by looking at these equations and defining this vector, I've basically combined the observer and the system and the controller in the closed loop. So this is all we got here. If I define this as a TSA, for example, the whole augmented system, this is going to be AA, BA, CA, DA. You can open up Simulink and just create the whole structure, but I'm going to skip that part and I'm going to just use it via code. So there's something that we still need to do. Let's look at help LSIM and see if we can, yeah, there we go. We can use LSIM here. So let's do that. It should be XT and then LSIM. And we give it this system here, TSA, and then the input time vector, and then initial conditions. So initial conditions is going to be important for this case because that will cause the difference here. So let's say the system states are at 10, 10, and the observer states are at 0, 0. Let's have the time vector 0.1, 0.1 to 10 seconds. Let's have u equals 1's size t. That should be it. And let's see if it's simulating our system, if we mess up stuff or not. Seems like we again did manage to mess up here. Oh, it's because of this whole thing. Let me just comment this out. There we go. So let me create a figure. CLF. Now, subplot, maybe 3 rows, 1 column. First one, hold on, grid on. And then plot, basically, t comma x, the first one is going to be the actual system state. Let's have line width 2. And then also the third one, which is going to be blue, which is going to be observer state. And let's repeat this for state 2. This is the second state. This is going to be the second state of the observer. And let's also have the output here, which we didn't actually create now. Y is equal to CA1 times X1 plus 2, 2, 3, 3, 4, 4, plus dA times basically U. That should do it, hopefully. And let's have Y as the system output. Yeah. And we can also maybe have the input here to see what's going on. What is the size of X? Oh, yeah, of course. Now, if I define, if I use the transfer function like this, then I'm not going to be able to acquire the states here. So what I'm going to do is I'm going to give it an identity matrix. We've done this before. So 4, 1. And there we go. If we didn't mess up stuff. This is basically it now. So 10 seconds of simulation time is a bit much. I guess we should maybe use 2 seconds of settling time, simulation time. And even less than that could be used here. So we see that our actual system state starts at 10, goes slowly down here, and our observer starts at the wrong direction, and then it's kind of estimates it, and it has a 0.2 settling time. It takes quite some time to estimate that. So we get basically the estimation here. And the same goes for the second state here. Our observer is way too aggressive, doesn't predict it well. It just surpasses it, and then it does its job, and we get 0.2 here. And for that reason, our output is also driven way off the charts, where we're basically applying just input 1, and we don't really get what we want here. But then eventually it kind of does what it is trying to do here. But you can see that the observer is quite important, because actually the system goes too much up, too much down, and then it tries to come and reach the steady state value that is probably something like, what is it now? It's tending to 1, but I would argue that it wouldn't reach 1. So what we can do in this case is that we could say we are a bit too aggressive here. So here we design that. Here 40 seems to be an overkill. Let's go with 20, even 10 maybe. Let's slow down it a little bit to see if it's going to behave less aggressive. At least we don't reach 200s now in the state estimates. It can be even slower. Let's choose, for example, 10 and 10. Yeah, it's kind of there's kind of a trade-off here. Of course, the states, the initial values here, they are also a bit high. If they are not that off, you can see that hopefully the estimates, they become also less off as in terms of values here. Let's see what happens if we don't have an initial state for the second state, for example. If it's starting from 0, you can see it still takes some estimation here. What happens if it's exactly equal to 0? Then you cannot distinguish it, basically, because it is on top of each other, because it starts at the same point, it goes like that, and you can see our actual response is basically this one here. So this is also the trade-off here. We can see that if we would use the actual states as for the state feedback, it would look like this. When we use an observer here, then we kind of lose this accuracy for quite some time. So yeah, it is important to note that everything comes at a price. When you're using an observer, even though this is a linear system and this is not an important one, then you might want to look for better choices. Of course, in our scope, this is enough for us. So you should know the basics here, meaning that you should know how to design the Luenberger observer. You should know how to design a state feedback controller. You should know what observability means, what controllability means. And you should know that how to maybe prove the error dynamics here and why we are assigning A minus LC, A minus BK, and all that stuff. But it is possible to optimize this. You might want to use some little script here that looks at the difference here, or uses the error signals for both of them, and then maybe take the RMS values of them, or integral square errors, and then try to minimize that. Or you might look for optimal observer design or optimal controller design, or even both of them simultaneously. And there are some PhD or master degree lectures, courses that deal with these stuff here. For example, LQR is a nice thing to use for control. With an energy function, you try to minimize a certain energy function here that corresponds to state feedback, but in a optimized way, basically. And there are also some robust control techniques to design both the observer and the state feedback controller to, yeah, well, have a better, in quotes, of course, a better response, or better controller, or better observer. Well, this is basically it, what we can cover in just one lesson about all this stuff here. You might go ahead and use Simulink and build your system, and then maybe put in a transfer function, put in the observer, and try to estimate the states. I would highly recommend you to try that part out, because I'm using code and I'm just generating the stuff, but Simulink would be more believable in that case. I'm going to upload the PDF, which has plenty of definitions, and also maybe the parts here. You can see that you can just do the transfer function conversion also using these equations here, and you can see that there's a right half plane cancellation, and you will end up in 2 divided by s. There's also the part where we design a p-type controller, or we're trying to design the state feedback controller, but we fail because of the non-invertibility or the singularity in the controllability matrix. Then we come up with our own state feedback, which is just to exemplify stuff. You will not need to come up with your own reduced version of the state space representation. Then we can see that they basically mean the same. We convert the transfer function into a state space model. These are the steps basically. And yeah, this is PDA. We design a controller. The state feedback controller is this. This is the closed loop. Then we look at A minus BK, and we get the poles here. We do the same, and we have the closed loop here for the p-type controller. Here's the duality of A minus BK and A minus LC. Here we have a response where we have the p-type controller and the state feedback controller compared in a single plot. You can see that this is basically the Ackerman formula for the observer design. And then we also have an observer here. You can also use Acker or place or commands like that, but I would suggest you to go along with this piece of code here using the symbolic toolbox so that you can learn it a little bit better. And then you have basically also the piece of code that demonstrates you how well it estimates. I guess this one is open loop here. Yeah, this doesn't have the control in it, but here in the video I've shown you the controller plus observer feedback. So this is just estimating stuff, but the one in this video also tries to control the system based on the estimates. So hope that this was a helpful session. And this is also basically our last session here. And yeah, see you in the next video probably. And yeah, that's it.